Let's try to draw the Lewis dot structure for ozone O3. We know the total number of valence electron for ozone will be 6 times 3, which is 18. And how many pairs are there? 9 pairs. So how to draw that one? First we will draw 3 oxygen, right? And we will connect them with single bond first, and that means I used 2 pairs out of 9 pairs. I am left with 7 pairs. So what I will do, 1, 2, 3, 4, 5, 6, and I leave the other one with the central oxygen. And now when you count the number of electrons around each oxygen, we can see that how many electrons are there for the first oxygen? 2, 4, 6, 8, octet complete. And here 2, 4, 6, 8, octet complete. What about the central one? 2, 4, 6 only. So octet is not complete. So what we will do normally? We will change one of the lone pair and we will make it as bond pair. So how many are here now? 2, 4, 6, 8, octet complete. 2, 4, 6, 8, octet complete. 2, 4, 6, 8, octet complete. So is there any other way you can draw it? So this is one of the way here you can see, right? So is there any other way you can do it? Of course you can change the position of the double bond to the other oxygen. So you will get another structure for ozone that again satisfy the octet rule, correct? So that is this one. So you can either go with this one or you can go with this one. So which one is correct? Both are correct. So they are called the two possible structures for ozone. That is called resonance structures. So the combination of these two resonance structures can be represented by this method. So the bond between both oxygen will be in between the double bond and single bond. So the bond length will be in between single bond and double bond. So that's the way you can recognize whether it is forming a resonance or not from the word questions. So they will mention the bond length is in between single and double. So you know that it is forming a resonance structure. And see that the way you are representing the resonance structure by putting a double-headed arrow here. Okay. All right. Let us try another example for NO3 negative. So for NO3 negative, total number of valence electron nitrogen 5, oxygen there are 3, so 18, and 1 negative. That means we have to add 1 electron. So you can see that there will be 12 pairs. And then when you draw that one as normal, nitrogen is the central atom, and oxygen and oxygen and oxygen. In this case, you can see that octet is not complete for nitrogen. So we will try another structure by shifting that lone pair as bond pair, right? So you can get, actually there are 3 oxygen, so you can actually draw 3 possible ways, and in all cases you can see the resonance completed. So all 3 are good structures and we call it as resonance structures for nitrate ion. Here is another example, NO2. Total valence electron, count them, and you can see the number of pairs and try to draw. And you can see that when you draw like this, octet is not complete, correct? So we will try another structure. That means the lone pair changes to bond pair in one oxygen here, in the other case to the other oxygen. In both cases, octet satisfied, and that is a resonance structure here. And the combination, the bond length is in between single and double bond. And now I want to point out one thing here, because we are dealing with a single, double and all, and we are talking about the length is in between single and double bond. So what's the order of single bond, double bond and triple bond? So single bond is the longest and it is weak. because it is long, so it is weak. And double bond in between single and triple. And triple bond is the shortest, therefore it is the strongest bond between the two atoms. And now try carbonate ion by yourself. Okay. So how many you are expecting? Maybe there are 3 resonance structures which all will obey the octet rule. Let's see a different one now. More than one central atom. How will you draw? We were dealing with only one central atom. Now let's see a molecule with a more than 2 central atom. So here the example is acetate ion. Acetate ion can appear as C2H3O2 negative, or sometimes it can appear as CH3COO negative. All are same. Okay, so let me try to write the structure for this molecule, acetate ion. You can draw 2 acetate ion structure. Maybe you are thinking, why is it not bracket and negative? But both are okay. This is negative charge, this is negative charge. That means what? This ion has a negative charge. Where is that negative charge going to? To the oxygen. So that oxygen is the reason for the negative charge on this acetate ion. So you can see that there are 2 central atoms, 1 and 2. 1 and 2. Only difference here is this first one is remaining same, no change, but the second one, the double bond on between oxygen and carbon is changing. So here it is and here it is. In both cases it is okay. Only thing is the negative charge is shifting from one oxygen to another, but as a whole molecule that negative charge will remain there. And now let us see there are the 3 structures, the possible structures. Okay, the possible structures, Lewis dot structures for SO2. So when you count the number of valence electrons and divide by 2, that will be 9 pairs. So as you will draw here, the first attempt is going to be like this. So I can put one more here. So 1, 2, 3, 4, 5, 6, 7, 8, 9 pairs. 3, 4, 5, 6, 7, 8, 9 pairs here. And 1, 2, 3, 4, 5, 6, 7, 8, 9 pairs. And here 1, 2, 3, 4, 5, 6, 7, 8, 9 pairs. So you can see in all cases we satisfied with the 9 pairs, and in all cases he said, let's see octet is following or not. Okay, so how many are here? 2, 4, 6, 8, 10 here, and here 2, 4, 6, 8, 2, 4, 6, 8. In this case 8, 6, 8. In this case 8, 8, 8, and 8, 8, 8. Correct? So how do we know which one is correct? By just looking at the octet, we may say this is correct and this is correct. Right? So let's see how to decide that one. So we use a term called formal charge for finding the best possible structure if there are more than one structure available. So how will you calculate the formal charge? The formula is number of valence electron minus number of lone pair electron minus half of bond pair electron. This is the formula we are using. So for SO2 molecule, the one we were talking about earlier, so in all these cases, we calculated how many 8 electrons, octet completed or not, how many electrons around each element. So all 8, and here it is 10, and here it is 8. So in this case, when you calculate the formal charge for sulfur, the valence electron 6, and minus 2 lone pair electron, which is here 2 lone pairs, and minus 4 because half of the bond pair electrons, 1, 2, 3, 4 here. So that equals coming to 0. So as we read here, structure with the lowest, preferably 0, formal charge are more stable. Okay, so in terms of sulfur, it is looking good. And now let's see for oxygen. The valence electron 6, and we can see that there are 4 lone pairs, 2 from here and 2 from here. So 4 lone pair electron minus 2. Half of bond pair electron means minus 2 here. So that is also looking good. So maybe this is the most stable one. Let's check the other one. So when you calculate the formal charge for oxygen in the second structure here, again the valence electron, there are 6 for oxygen and minus 2 because of actually it is not minus 2. Valence for the sulfur, yes, for the sulfur, yes, 6 minus 2 here and here 1 2, so minus 2 will be 2, half of bond pair electrons. So this is coming, formal charge for sulfur is coming 2, correct? Formal charge for sulfur is 2, and for oxygen it is going to be negative 1. If you calculate in the same way, this is going to be negative 1, and this one also look the same in terms of lone pair and bond pair. So this is negative 1, this is negative 1. So the formal charge is not close to 0. When you compare to this one, this is the perfect one we can get. So this is not the structure we are going to accept. Similarly, if you calculate the formal charges here, the oxygen will be different here because it's not looking good. I mean, looking same here on both sides. So one side oxygen equals 6 minus there are 4 lone pairs minus 2 bond pair, because 4 divided by 2 is 2. So I just count the bonds 1 and 2. So it is going to be 0. That is perfect. But for sulfur it is 1. This is 0 and this is negative 1. Correct? So I have a best one, which is the first one, and then why am I going with, I don't have to compromise. So since we have the best one, so this is going to be the more stable, when we will accept this one. You can try this one same as this one, so it's not going to make any difference. So that's the way we decide if there are more than one equivalent Lewis structure, okay, that can be constructed for some molecules, such as here the example we took is SO2. Here is another example. Draw the possible structure for XeO3, an explosive compound of xenon. So calculate the formal charges. So in this case, we can see that octet is complete. And for a baby chemist, we will say what? This is okay. This is correct. The octet is complete in all cases, 8 electron, 8 electron, and 8 electron. So we will be happy with that. But in AP level, what we will do, we know how to calculate formal charge, and we know how to make the best structure out of it. So what we will do, we will calculate the formal charge, and when you calculate the formal charge for xenon, you can see in this case there are 2 lone pairs and the valence electron 8 minus 2 minus 6, 1 2 3 4 5 6, so it is going to be 0. And for oxygen it is going to be 6 valence electron minus 2 here and 2 here, so 4 lone pair electrons and minus 1 2 half of bond pair electron. So that is going to be beautiful. This is the best stable structure for xenon trioxide, correct? So in this case, we can see that formal charge is not as perfect as in the second case. So this is what we are going to accept in AP level. This is not that stable. So this is just the basic structure. So we will not accept that one, and we will accept the second structure.